Our next speaker is Stefan Kaufmann, who's the founding director of the Max Planck Institute for Infection Biology in Berlin, and has played really a major leadership role in the area of TB and HIV infection, really throughout the course of these epidemics. He's also played a big role in South Africa with the Max Planck Institute. They're getting involved with the KwaZulu-Natal Research Institute for TB and HIV, where they now support faculty members there and are really boots on the ground then in terms of research being done in Africa. So Stefan, thank you very much.
Well, thank you so much. Thanks, Bruce. Thanks, Anna. And thanks, everybody, for being here. Particularly thanks, actually, that you allow me to speak from the basic research perspective. I would say the naive view of a researcher who thought that basic research can make some changes in the control of TB and HIV. And I think that this has actually become a more broader attitude to it. Even Nature in March this year had an article on intervention measures and our failures to control TB, malaria, and HIV. I won't go into the data. I guess most of you are well familiar with them, and will directly go into the major topic of today, and that's biomarker research. And I will start with some critical introduction. I hope you forgive me. So this is a kind of a terribly complex overview about tuberculosis. We don't have to look at all details. What I just would like to mention, of course, we have a number of sources of samples that we can use for biomarkers, and I will only focus on two of them. Breath and sputum, of course, and sputum is obviously the most conventional one, although more and more activities are looking into electronic gnosis on giant rats in sniffing tuberculosis. And indeed, in our collaboration, which I will not discuss today, with Apopo, we identified a number of small molecules. So I became a full believer in this kind of sometimes considered as voodoo-like activity. So it works. Then, of course, urine is a very practical source, and then the major source is blood, and I will focus today on transcripts and metabolites today. Now, what I would like to point out here, actually, is the issue what happens during tuberculosis, and how confident can we be that we really look at the right things if we look at the blood or any other external source for a disease that's really manifested in the lung. So someone coughs, someone gets infected, and then small lesions will develop. I'll be very simplifying at this stage, solid lesions, and these individuals remain healthy. Now, these are about 2 billion people in the world. They remain healthy, but they contain the bacteria. Now, in 10% of those, the lesions then become necrotic, caseous, disease develops. The point I would like to make here is that at both stages, in the latent TB infection, healthy, 2 billion, and the 9 million cases that develop every year, there is a good chance that at least partially the containment or the disease are controlled locally through autonomous mechanisms. And those we miss if we look at the blood or any other source. Keep that in mind. And the second point I would like to make is that its disease is really a complex continuum from solid granulomas to necrotic to caseous granulomas. This has been long known or speculated by research done more than 100 years ago in the pathology departments, and has been revitalized more recently. And obviously the wonderful work of Sarah and Joanne Flynn have contributed to a better understanding in a non-human primate model. So what I want to say is that we have all different stages, the more healthy like solid granulomas, the necrotic granulomas, and the caseous granulomas. And it really is a mix of all of them. And what you measure in the blood is a kind of median that you measure as a response to this. The second point I would like to make is that with biomarkers, we currently are in an early stage, and I'm only talking about host biomarkers. We look at cases that have been defined, diagnosed by the clinician. We look at healthy individuals that have been defined, let's say, by IGRA or other assays to be latently infected or non-infected. What we are still looking for is a marker that's independent and better than the clinician. That is still what we are missing. That is at this interface from latent infection, healthiness, progressing into disease. And we have many cases where the clinicians told us today these people are diseased, they have active TB, and they are right. But 6 weeks later, they tell us they return to normality. This was considered a kind of sacrilege earlier times, but now we know it's true. And that's very simply explained in that scheme, although again, and that's my failure often, it's oversimplified. Let's assume you have a caseous granuloma that enters the alveoli, then you see acid-fast bacilli in the sputum. And this is gone, and now the other granulomas are away from the alveoli or still contain, and then you would not diagnose that individual as an active TB patient. So this is all much more complex and all more fluid, if I may say, volatile than at least I had originally thought. So let me talk about biomarkers on 3 aspects. First, biosignatures, which is a composition of biomarkers, we'll come back to that, for differential diagnosis, host responses that can distinguish reliably tuberculosis from latent infection, and notably at this kind of interface of progression from latent infection to active disease. Ideally, you would have something like a point-of-care diagnostics, not easy, but I think achievable. Second, and that is now the researcher speaking, we want to understand biology and pathology on molecular and cellular levels, and therefore we want to use and exploit biosignatures, biomarkers, to better understand what's going on in disease. That's a large program in our institute where we take knockout mice with knockouts for certain markers that are particularly relevant, in our opinion, to better understand what that marker is going to do. I'm not going to discuss that today. And then what I would call the holy grail of TB biomarker research, biosignature research, is a marker, a signature that can predict disease reliably in latently infected people. So who will develop disease tomorrow, 10 years later, who is latently infected? It's the 3 to 5% of those who are latently infected and will develop disease, very similar to markers or signatures that are now being developed for cancer diagnosis and prognosis. The starting point was very simple. What we did is just very simply take 2 populations, 2 billion people in the world latently infected, and take the 9 million people every year, 8.6 whatever, who have developed disease more recently or for quite some time. So we compare biosignatures in these populations as a starting point. I will talk today mostly on transcriptomics and a little bit on metabolomics, and start with the differences which I term biological and diagnostic signatures. As you will see in a minute, these are not the same. We'll talk about robustness and specificity. Mind you, we are in early stage, and talk about sizes of signatures. Should they be very large to distinguish, or should they be rather small ones? And what I consider important, how we should stratify our signatures to get the most reliable results, knowing, and this brings me for the first time into the field of HIV also, that TB is not a standalone disease. It is taking place in Africa with many other diseases co-occurring, with the most important one, HIV/AIDS. So let me start with one strategy, which is not really for a kind of point of care, but we thought, this was not our first study on biomarkers, but we thought it's worth to do it, and indeed it is worth to do it, mostly also if you think of iris. So we select T lymphocytes, the mediators of protection, including CD4 T cells, the reservoir of HOE, and CD8 T cells, and look at the selected T cells and the markers that pop up there in latently infected versus active disease. And it came very soon clear that there was indeed a biological signature composed of the IL-2 receptor, JAK3 STAT pathway, And that also included some other related genes in the regulation of immunity, adoptive immunity, T-cell immunity, and that's MYC and PIM1. I'm not going into details, just wanted to tell you that this is a biological signature which indicates immunosuppression in TB patients because of that pathway. And then we looked whether this can also be used for diagnostic purposes, and indeed it was. If we took IL-2 receptor alpha in a relatively medium-sized population in Cape Town and Stellenbosch, IL-2 receptor alpha, JAK3, SOX3 as discriminating markers, and then also added MYC and PIM1, we got about 98% reliable diagnosis of TB versus latent infection. Remind you, this is, we confirm what the doctors, the clinicians told us. And if we looked at LTBI versus non-infected, whenever I use the word non-infected, I mean non-MTB infected individuals, we got even 100%. So this is very promising. The problem is that we had to select T cells or lymphocytes. We see this in both CD4 and CD8 T cells, indicating that similar mechanisms on this level take place in both T cell populations. And now you could say wonderful biosignatures, which are a kind of biological stream sequence, are good for diagnosis. In this case, it's right. Still, I would be a little bit more careful. So there are many other, or not many, but a number of other biological signatures, that is gene sequences that are all activated, and it makes sense if you look at the map of all the genes, you see this is a sequence. If A goes up, B should go up as well, because B depends on A. These are the IL-2 receptor JAK3 STAT3 signaling pathway, as I mentioned. The most famous probably nowadays is the type 1 and type 2 IFN pathways, where Enogara's group showed nicely that IFN signaling pathways are differentially regulated in active TB patients versus latently infected. And probably the first signature was actually described by us in the 2007 paper, one of the first TB biomarker papers, where we showed that Fc gamma receptor signaling pathways are also upregulated in TB. So biological signatures are nice. They are co-regulated, they make biological sense, and they are useful for better understanding of host responses. I would, however, argue, despite the data I showed you, that often they show lower discriminatory power because these markers are correlated. So if A goes up, B tells you, biology tells you B should also go up. Let's just assume you're sitting in a committee deciding on an NIH grant or a PhD thesis. There is number A, that is the individual who knows the work best, so he has a 5% error rate. That is 95% of what that person says was most likely correct. And then there are some other reviewers, 10% error rate, and one is particularly ill-prepared, 20% error rate. Now this gives, if you look at it all together, already only a 1% error probability. Now let's just assume that this person, and that happened even to me every now and then, and probably also to you, thinks I'm not really well prepared, I'd rather follow the guidance of the one who presented the whole work. And therefore, number E follows A, and then you have a 1.5% error rate. And the others then also think, let me follow the decision-making person A, then you have a 5% probability of error. What I wanted to tell you is, and that's very simple, to single biomarkers. Single biomarkers are independent at all together reduce the probability of error. Biological biomarkers are correlated and they do not as much contribute to the significance discriminatory power. So we went on actually to go for differentially expressed markers which are not related. This was biologically not as nice, but I think it's the way to go if you want to be as simple as possible. Unrelated markers, take the best and do a custom-made signature. The markers we came up with is most constantly both in Europe and in Africa, and probably also in Asia, not studies by us, but I'll come to that, is Fc gamma receptor only. Lactoferrin, iron uptake, you know that Mycobacterium tuberculosis needs iron, we need iron, so there is a competition. Then clearly GBPs, guanylate binding proteins, you can take one or two. a number of them. They are very similar in their behavior. And then you can add also granzyme A killer molecule involved in cytotoxic T-cell responses, and defensins involved in antibacterial defense against intracellular bacteria, amongst other things. So if you look at the very first study we did in Germany, we got with these markers Fc gamma, lactoferrin, and one other one, Rep33, which I won't discuss today, a kind of reliable diagnosis of TB of 88% compared to the clinicians, and LTBI, latent infection, 91%. Then we went into Africa, South Africa, Uganda, and the Gambia. So the Gambia, as those who are in the field, and Uganda are very different with respect to the mycobacteria that are prevalent there. Mycobacterium africanum is quite relatively prevalent in Western Africa. It's missing totally in Eastern Africa. And yet, we can distinguish in either of these situations tuberculosis from latent infection. If we use, again, Fc gamma, lactoferrin, GBP5, granzyme, about 94 to 90% differential capacity, diagnostic capacity. And we can further slightly improve if we take 1 or 2 defensins to about 95% correct diagnosis, as was told by the clinicians. There's a very nice study recently by Mike Levine and colleagues that was using a similar approach, larger signatures, but very similar in a sense that these transcripts were unrelated from each other. So a diagnostic signature which allowed them to diagnose tuberculosis highly reliably, even in the presence of HIV co-infection or with or without HIV co-infection. So it works. Is it robust? Well, we did a lot of comparisons recently in comparing our own data with those in the literature. And one of the first comparisons, obviously, was the one with Anogara studies, which used actually TB patients in Great Britain, mostly foreign-born individuals. 74% of those transcripts they used for diagnosis also were able to diagnose in our case. So we have an overlap. If you take the study in the Gambia, the study in South Africa, compare it with the British population, 74 TB population, obviously, 74% identity of those markers that were up or down regulated. If you only look at the Gambia and the British population, we can add another 13%. If you look at the South African group and take the British study, 5% can be added. What I wanted to say is this seems to be robust. Different populations, different lab workers, different assays, different funding, if that plays a role at all, and still similar results. And actually it must have been convincing, because even the Gates accepted that as something to go on with our grant, if I come back about that in a minute. So it seems to be robust. More recently, we went into other studies. These are our studies, and I just show you one of the guanylate binding proteins, GBP5. You see it's upregulated in those studies which we looked at. It's also upregulated in the study by Mike Levine, and study from Anogara, and also other studies, Tom Ottenhoff studies. And this is true for a number of markers that we use now for custom-made signatures. So they are unrelated markers. They don't make a biological story, but they're the most useful for diagnosis. And it even works in the study of Mike Levine group on HIV co-infected TB patients. And that's the controls in gray, where you see that these are always differentially accurate. This is just an example for a number of markers that we need. Alone, they are insufficient. So it's robust. Is it specific? Now, this is a very difficult issue, which I had a lot of discussions or even fights on. We can distinguish latent infection. We can distinguish uninfected TB, MTB, uninfected from TB. But what about other diseases? In the beginning, I thought this is a kind of a killer argument. There will always be another disease. I think we can get around it. So we chose sarcoidosis, which, as many of you know better than me, is a very similar disease, pathogenesis and pathology-wise. Yet, most people would agree it's a non-infectious disease. At least it's not related directly to Mycobacterium tuberculosis. Can we distinguish TB and sarcoidosis? sarcoidosis with the markers we and others have at hand to distinguish TB from healthy individuals? The answer is yes and no. So first let's look, this is the study, and what you see immediately, more than 8,000 genes are jointly differentially regulated, both in sarcoidosis and in TB. So there is clearly a marker, a kind of a shared marker set that is indicative for both sarcoidosis, TB. Yet there are still enough markers that you can use to identify TB and distinguish it from sarcoidosis. Now these are the markers that compare disease versus healthiness, either TB alone, sarcoidosis alone, or both. So the message is, indeed, there is an issue if you go for similar diseases. Now, this is not saying that sarcoidosis is a major issue for diagnosis of TB in Africa. That's not the point. The point is, are there similar signatures in different diseases, and how can we get around it? Now, if we look at the transcripts of the Anogara paper, 393 transcripts were called TB specific, 86 were TB specific core signature. And what you see, yes, 75% in our study of the genes differentially regulated belong to this, or 77 to this group. The issue is that this also holds true for sarcoidosis genes. 76% of the sarcoidosis genes differentially regulated in sarcoidosis were in that signature, 85 in that signature. So you have to be careful. It's not sufficient to look at TB versus non-TB. It's also to consider other diseases. There is a way around, clearly, because there are still, as I said before, still enough genes that you can use. It's not the same. So what you do is you have genes that distinguish healthiness from disease, be it TB or sarcoidosis, and there's another set of genes which you use to distinguish between different diseases. And that's the major point I would like to make. And that's not so strange, you know. I mean, the immune system is not made to have a specific response for any disease on the world. The immune system could just not cover that. So what we have to think of is that there is a shared immune response, let's say CD4 T cells, not important here, just as an immunology example. And then there are some specific genes upregulated in TB, differentially regulated, some in sarcoidosis, and we looked also at systemic lupus erythematosus or in others. So more is not always better. I was often criticized when I said I think 5 to 10 genes are better than 50, 60, because in simple thinking, you would say more is better because you have more parameters to distinguish. But the problem is the problem of overlap. So it may be good to have a large number of genes to distinguish healthy and TB, but clearly not if you go for other diseases. And there's an easy way around. There's nothing new, actually. You use an algorithm. Ultimately, you may use 50, 60 genes, but you don't use them at all in the beginning, but rather in algorithm where you, let's say, and that's just my own dream, distinguish inflammatory responses from healthiness, chronic inflammation from acute inflammation, and so on, and ultimately go there. You don't even have to do that in the wet lab. That can be done by the computer. What I wanted to say is use an algorithm rather than saying there is a large gene signature which allows us to distinguish the different diseases. That probably doesn't work. Okay, I want to make one small comment on a study that we are just currently developing, and that is looking at signatures in different cell populations, because I think later this will become important if we think about signatures that can help us in predicting iris or not and other issues. There we won't get along with peripheral blood cells. And we used a system where we looked at patients with active TB prior to chemotherapy, patients with active disease post-chemotherapy, and compared those. Now, this is an ongoing study. I just don't have any data. What I wanted to tell you that it works in principle, proof of principle. So we can separate by max at difficult situations CD4, CD8, B lymphocytes, NK cells, monocytes, neutrophils. We look pre and post treatment. We don't look at relapses at this stage. All are cured by definition of the clinicians. And we wonder now whether we can distinguish different markers that are going along with different cell populations. Now, the important thing is here, just without going into details, what we do here is we compare differences of differences. So we compare in T lymphocytes or CD4 T lymphocytes pre-post. And we take the difference between pre-post and compare that in the different cell populations. And what you see here clearly, and that's just to give you a kind of feeling, neutrophils, monocytes, NK cells, B cells, CD8 and CD4 T cells can be easily separated if you use appropriate principal components. That is a cluster of genes that are differentially regulated pre and post in neutrophils or the different populations. Just one example, another guanylate binding protein, GBP6, is clearly upregulated only in neutrophils. CXCL12 also only differentially regulating neutrophils. Again, this is difference of difference pre-post. And here's another example where you see myeloid cells, apolipoprotein 6 or caspase 8, only differentially regulated pre-post in the myeloid population. And we have other subsets or genes that are differentially regulated in the lymphoid populations or even CD4, CD8. Also there it is not as clear. So clearly I think the neutrophils and mononuclear phagocytes, monocytes, are the best suited cells for these studies. Let me now come very briefly to the prognostic studies. Why do we want a prognostic marker that is a marker that tells us today who will develop disease tomorrow, talking about latently infected individuals? Prediction of disease, that's what we want. And why is it good? First, prediction of disease. Second, stratification of study participants for TB vaccination of latently infected individuals. It would make, even if you are don't have a very exact data, but if you can reduce study populations by identifying those who are at highest risk for a vaccine trial or also for a drug trial, preventive drug trial in that case, by 50%, you will save 50% of the dollars. And that makes it, if you, let's say, can even be better, let's say 20%, 80% less cost. And that is a major factor in these clinical trials. It can also be used for monitoring of clinical trials, although I think the stratification is the more important one, and obviously for prognostic diagnosis, who, as we just heard, gets the INH, because you would like to deliver the INH either to risk groups or to those who are likely to develop disease as indicated by such a prognostic marker. The study we have started many, many years ago in the GC6 consortium now seems to be coming to an end, although the data are still not ready. This is a study with 7 different sites in Africa, and I will mention 3 sites here: Tigerberg, South Africa, Addis Ababa, Ethiopia, and Banjul, the Gambia, where most of the study samples were collected. So the study goes like this. Someone coughs, diagnosed as TB patients, household contacts of this index case are being asked whether they can be enrolled into the study. Blood is taken immediately after diagnosis of the index case, 6 months, 18 months, 24 months later. Enrollment has been completed already in 2010. 4,500 household contacts have been recruited. Originally, we were also very ambitious going for HIV positive. We left that out because ART treatment became, which is good, but of course could have disturbed the study, so we gave that up. Follow-up had been completed in 2012. It's a 2-year study, and the analysis actually started a couple of weeks ago with the Metabolomics studies, and now also the deep sequencing will be done by BGI with the Gates Foundation's funding so that we can analyze them. Now we will analyze them, and separately Alan Adderham's group at the Seattle will also analyze. So we have about 80 TB cases. That's about 3% that were non-protected. We will find the markers, hopefully, that are differentially regulated in this population versus that population. And we hope we find the markers, let's say, at 6 months, although they will develop disease 10 months or so later. So this is a short-term study, but it gives you the indication. I hope that actually the data will be ready next year. I may have said that before, but now the data are really at the sites where they are being analyzed in the wet lab, and we can analyze them. At least the metabolomics data will be available by the end of the year. 3 more minutes, or metabolomics? Okay. Metabolomics. We embarked also on metabolite studies, although this was a minor project. We thought it is worth, particularly actually for drug treatment studies, to look also at host metabolites and see whether we can use host metabolites to differentiate between diagnosed TB patients, differentiate them from latently infected individuals. The reason really was originally that I thought, and that was far too naive actually, that you could have a kind of a dipstick sooner or later where you have biochemical reactions that tell you whether someone has TB disease or not. Reactions like a dipstick for urinary whatever infection, diabetes and so on, but on host markers. So about 400 in the 3 studies, about 400 compounds were analyzed, all done by Metabolome. They're very good. They were analyzed. Some of them remain unnamed. That is, you have a spectrum, but you don't know what it is by name. That is, you can't look in the biochemistry book, but the spectrum clearly tells you this is a unique chemical identity. And what you see here is, yes, it works. Of 38 TB patients, 37 were correctly diagnosed by metabolites. Again, comparison clinician versus metabolites. In the second study, 44 of 48 individuals with active TB clinical diagnosis were correctly predicted by the metabolic biomarkers. We need about 15 to 20 markers. This is numbers of markers that were analyzed, and this is the error rate, and you see here about 5% error rate. 15 to 20 markers are sufficient to get a 95% correct prediction. What are the markers? These are mostly hypoxia-induced inosine methionine, which are anti-inflammatory, so this can also tell you some story. Fibrinopeptides, indicative of the fibrotic lesions that are prevalent in granulomas of TB patients. Lysophosphatidyl-cholines, indicative for a lot of cell death. We can't say whether it's apoptosis, necrosis, it's also known, but you see that reflected in the serum of patients. And finally, a lot of tryptophan metabolism, kynurenines, hydroxykynurenines involved in the tryptophan metabolism. And you know, in immunology, tryptophan, IDO, perhaps to make that clear to you, is something that's very well associated with immunosuppression. Let me end now with a kind of a simplified scheme. This is a Chernow phase. This phase is made on the basis of the different markers. Let's say in our case, the metabolomic markers. So the size of the head is component 10. The size of the chin is the T5, component 5, face of the shape C2, and so on. So we use about 15 of these markers, which we identified before. I told you 15 markers are sufficient, metabolites are sufficient. So we look at that and make a face because it's much easier to recognize faces than biochemical entities, unless you are a real chemical freak and you know all these compounds immediately as if they were your children or so. I'm not. My father was chemist. Okay, now we sort these faces, and what you see, there are these terrible looking. Now this is defined how we choose which marker is responsible for which part of the face. But the interesting is, if you look at those 2 upper rows, they look quite heterogeneous. Those look much more homogeneous. And guess who is what? The upper ones are active TB patients. These are TST positive, and these are TST negative. That is infected healthy, non-infected healthy. What I want to tell you is the heterogeneity in the metabolites is reflected here. What I told you before, different granuloma types and different composition of solid versus necrotic versus caseous granulomas play a role. This is without HIV. And still you have these differences. And I think I could best start perhaps with a citation for Leo Tolstoy. Happy families, and there's a sense behind it, happy families are all alike. Every unhappy family is unhappy in its own way. What it tells you is that being healthy is a much more congruous, much more shared activity. TB is a complex disease. It has a lot of differences. And now add HIV to it, add iris, drug treatment on it, and you will get even more differences. Now, these are the people who did the work. Jaron Matzdorf in the wet lab, General Weiner in silico were involved in the biomarker studies. These are other people in the biomarker studies. And we did this all with the GC6 team, with the Gates Foundation support, sarcoidosis with Joachim Müller-Quernheim in Freiburg, and the metabolite studies by Adam Kennedy and Rob Mooney from Metabolome. Thank you.
I'm afraid in order to have a break that we only have time for just maybe 2 questions. Sarah.
Okay, first, can I add or not my question? The turn-off bases are totally fabulous. Oh my God, they are such a good way of looking at such bad data. So then, what do you think the next steps will be to finding markers that are going to tell us about mechanisms of protection, not just indicators of disease state?
Well, I think that is actually already in the table. I thought I'd talk about the biomarkers as we use them. For example, we identified microRNA 223 as a differentiating marker. Thanks God, someone at Boston Harvard University had a knockout on microRNA 223. We now understand that microRNA 223 is not only a marker, as already a molecule that controls maturation of monocytes and neutrophils, but also controls their migration into the lung. And what we see is more or less in absence of microRNA 223, we get enhanced influx of neutrophils and heavy disease. That's published last year. And there are 2 or 3 other studies in that direction. What I think is, and what I would like to call reverse translation, it's now the time, for the first time for me at least, that we can learn a lot from patients. So ultimately that the patients tell the mice what experiments they should undergo rather than the mice what the patient should do. Yeah. Simplified.
Yeah. Stefan, you mentioned in your prognostic work a discrete exposure to tuberculosis and then following forward. The real world is probably many exposures, reinfection. Are you seeing anything in your markers that would suggest that?
Well, as I said, the markers are not there yet by name, but you are totally right. This is an oversimplified scheme. You can decide it's too simple, I don't do it. We decided it's simple, but we still do it. Clearly, you are right. We exclude those who develop TB during the first 3 months, assuming that those may have acquired infection before the index case. But otherwise, these are household contacts. But as you know how field studies look like. These are household contacts. Still, they go to school. They could get it elsewhere or meet someone, go to work. Clearly, you're right. This is not the ideal study, but that you have to live. It's not a mouse study, and you know that.
Stefan, thank you very much.
Thank you.